Okay, you guys, I'm short on time. So I'm gonna do this maybe a little fast, okay? Because it was either that or I don't do it at all. Okay, let's do the 6-1 homework. And there we go. Okay, so here we go. It says, here's a table that shows the mass of a blob. We looked at so many blobs today. Nope, let's zoom it out a little bit. Okay. So, it says, what would the blob's mass be on day 2 if it grew linearly? So remember that linearly means we add the same number each time to get the next thing. So between 52 to 65, if this is growing linearly, we would be adding the same number. And you want to hang out in here? Of course. I'm doing a homework video. Okay, no worries. So we add the same number every time. So what you got to look at is, how did 52 become 65 if addition is the only operation we're allowed to use? And that's going to be plus 13, okay? So if the relationship is linear, then on day 2, the 65 needs to grow by another 13, okay? And it's going to become 78. Boop. All done. Okay, now it wants me to write a linear function to represent the blob's mass. You guys can do this the way I did in class, where I followed the table until we saw a pattern and yada yada. Or you may recall linear functions. Follow the equation y equals mx plus b, okay, where m is the rate, it's how much we change by each day, in this case 13, and b is our starting value, in this case 52. So f of x, our fancy version of y, equals 13x plus 52. Cool. Okay, now we're talking exponentially. Let's go back, and they're just like, wait a minute, let's redo everything we just did if we were growing exponentially. So now with exponential growth, what we have to look at is, what do we multiply to get from 52 to 65? And if you can't do this in your head, guess what? Neither can I, all right? Here's what we're gonna do. We're gonna take our calculator. We're gonna take that number, the second number, 65. We're gonna divide it by the number that comes before it, 52. And we're going to press enter, and it's 1.25, okay? So that means we are multiplying 1.25 each step of the way. So what's it going to be on day 2 if I am multiplying 1.25? I'm just going to take 1.25 and multiply it by 65. It's 81.25. Okay? Technically, there's units here, right? Grams. Let's put grams in there. Okay, write an exponential function to represent the mass on day x. Okay, so that's the equation, all right? Remember our exponential functions, a, b to the x, okay? Where in this case, b is our rate, and a is our starting value. So in this case, what we're growing by is 1.25, and our starting value is still that 52. So it's going to be 52 times 1.25 to the x. And remember, I told you I definitely prefer the b to have parentheses around it, okay? Number 5, the function a of t equals yada yada represents the mass of a blob t years after it returns to its home planet. Change one number so that. Okay, so right now we've got a function where our starting value is 126. And because this b value is greater than 1, we have growth. Okay, they want the mass to decrease, meaning they want us to have decay, meaning that our b must be less than 1. You can change this b value, that 1.26, to whatever the heck you want, as long as it is between 0 and 1. How's 0.9? Maybe 1/2. Maybe 7/8. Okay, I don't care, all right? Just don't go with a negative number. That doesn't count, all right? Moving on. The mass is 226 grams when the blob... Oh, we're changing a number so that the mass is 226 when it first returns to the planet, meaning that starting value of 126 needs to be 226, okay? So that's it. Just write that with a 226 there. Okay. And now we want the mass. Okay, I didn't write the equations because I'm getting lazy, but I feel bad about it. Here we go. We're going to have here y equals 126 times any of these. I'll go with 1/2 to the x or to the t. Over here, we're going to have y equals 226 times 1.26 to the t. And over here, y equals, we want it to grow by 6%. So please remember, percentages have no business being in your calculations. So you're going to grab that decimal point, you're going to shift it twice to the left before you even think about doing any math, all right? We're going to have 126. However, our new b is going to be 1. Growth means plus 0.06. So 1.06 is my new b to the t, and that's number 7. Okay, number 8. In 2005, the value of Kimura's house was that much. It sounds like an A value to me. Each year it increased, that looks like a 1 plus something, by 3%. So 0.03, okay? Remember, decimal moves twice to the left in a percentage. So what was the house's value in 2010? Round to the nearest whole number. Write an equation representing the value of the house as a function of the number of years after. Okay, so I'm going to do 9 first and then do 10, okay? So for number 9, I'm going to have the 150,000 times 1.03 to the x, and x is years after 2005. So 2005, it's going to be 150, and then each year after that, we're going by that number. So in 2010, x equals 5. It's 5 years after 2005. So I just plug 5 into here. It's 150,000 times 1.03 to the 5th power, which is going to go into the calculator like this. $173,891. Okay. Number 10, in 2015, there were 2,400 deer in this area. The ecologists determined that the deer population increased by 7%. Which function models it T years after 2015? So remember, what you started with, that's A. So that eliminates A and C because they don't start with 2,400. Then, because I'm increasing by 7%, I need 1 plus 0.07, okay? Remember, if B is less than 1, we have decay, not growth. And that's a number hecka less than 1, okay? These deer are like dying like it's like the zombie apocalypse, okay? These deer are growing by 7%. Okay. Sorry, it made me think of, what was that show, Walking Dead? Where the zombies will kill everything and then there was no like nice beautiful animals anymore because they all got eaten. Anyway, okay. Using the digits 0 to 9 only once, write an exponential function h of x that has the smallest possible value at h of 5. So that means like x is going to be 5. And we want the smallest possible number we can get. I don't think it even matters as long as x is any like positive number bigger than 1. Even 1. Anyway, not important. Here's the deal. This number right here, that's the base because this is A and this is B to the x, okay? I want the absolute smallest number that I can possibly get using the digits from 0 to 9. And the smallest that I can make b is the way to go. So I'm going to put a 0 in the first spot. And they told me my function has to be exponential, which means I have to put 2 in the second spot. You guys, exponential functions cannot have a base of 1 because then they're just a horizontal line, okay? So the smallest possible base that I can have is using 0 and 2. And now if I multiply whatever this will come out to be by the smallest possible number that I can, then I'm good. So the tens digit, I'll use the one that I couldn't use earlier. And for the ones digit, I'll use my next smallest number that I have, which is 3. That's my story, and I'm sticking to it. I don't have the answer key to make sure I'm right, but I don't know. Feeling pretty confident. Okay, we're going to change one number in each function so that it is translated up 2 units. Remember, up 2 means we need a plus 2 that is not in parentheses with x, all right? So look at that, minus 5. Get it out of there. Make it a plus 2. Okay? Look at this 6 right here. All right? Oh, wait a minute. What's the thing? Change one number. Wait, no. I misunderstood. Hold on. We want this function to go up 2 from where it is. So we need to just give it a plus 2. So whatever this function is, it will go up 2. Now, simplified, it's going to become 3x plus 4 squared minus 3. So technically, what we needed to do was, let's call it d of x, change that 5 to a 3, all right? And in this situation, to move whatever this is up 2, we got a plus 2 this guy, which means that it will combine with that 6 and be 8 plus 3x plus 4x squared, all right? This is a parabola. Oh, and whatever. Forget the letters being reused here. We'll call this f of x. How's that? We'll call this one g of x. All right. Okay, you guys, good luck. I gotta go. Bye.